Hi, this is Raphael Mudge, the creator of Cobalt Strike. This video is an addendum to February 2018's In-memory Evasion course. In particular, this video, we're going to go through the memory evasion specific updates to Cobalt Strike 3.11. In part 4 of In-memory Evasion, I introduced Cobalt Strike's model for thread emulation with in-memory indicators. It's a pretty simple set of ideas. Take Beacon's DLL and change its header to look like the header of a malicious sample as much as possible. And populate the Beacon DLL with arbitrary strings pulled from the malware sample as well. So that's Cobalt Strike's model for thread emulation with a memory-injected DLL. In part 4 of In-memory Evasion, I introduced some of the headers that you could set. Well, Cobalt Strike 3.11 expands these. You can now set the checksum field in Beacon's PE header. You can set the entry point value. You can set the module name because it is a DLL. And you can pull an arbitrary rich header into your Cobalt Strike Beacon DLL as well. The rich header happens to be metadata inserted by a Microsoft compiling toolchain. And that metadata happens to state which file or which programs were used to build the executable, how many files they operated on, and which versions of those files were used. That's about it. The rich header is kind of interesting because that was used as a false flag indicator by an attacker who tried to conduct operations against the 2018 Winter Olympics. Kaspersky Secure List happens to have a great article on this particular false flag indicator. And now you have it in Cobalt Strike too. One thing I'm aware of as a developer is that it's great you can change these fields in Beacon's header. Okay, I understand that's really great. You're really excited. But I also understand you're busy. And it is a lot to ask for you to find a program that can parse a PE file, pull all those values out, and format them in a way Cobalt Strike's going to accept. I get that. Well, to help you out, Cobalt Strike 3.11 introduces a PE clone utility. And this utility happens to ship with the Linux package of Cobalt Strike. What does PE clone do? It takes an executable or a DLL and it pulls out the various headers and values that Cobalt Strike can spoof and gives you back a block that you can paste right into your malleable C2 profile. Now, if you like and you want to see everything Cobalt Strike can pull out, you can use the dump verb to get a full dump of details using Cobalt Strike's internal PE file parser. So that's a PE clone. And we're going to demo that here in a second using a sample pulled down from my friend Silas Cutler's malware sharing website, malshare.com. All right, let's take a look at PE clone. Here we are in Kali Linux, and I have the HaveX profile from before. And at the end of part 4 of In-memory Evasion, we populated the HaveX malleable C2 profile with the strings taken from various YAR rules. And we did what we could to transform the header to look like HaveX. Okay? Pretty cool. Now, what I'm going to do today is I'm going to use a sample downloaded from malshare.com, and it's tagged as having flagged on a YAR rule for HaveX. And we're going to pull some values out of this particular sample and update our malleable C2 profile. So here I happen to have that file, C6, whatever. And we're going to use the PE clone file that comes with the Linux distribution of Cobalt Strike. So we're just going to do PE clone, C6, E6, so and so. And there we go. We get back a stage block that has the checksum, compile time, the entry point, the image size if it's larger than beacon, the actual exported name of the DLL, and the rich header, all ready to go. So that's all you've got to do. So we're going to go ahead and grab that, and copy that over here, and paste it right in our profile. And that's it. That's how you use PE clone. Now, some of these things are kind of redundant here. The transforms to replace the DLL name, we don't need to do that anymore. In fact, we can just get rid of the beacon name. This particular DLL does export something other than reflective loader, so we can update our beacon if we want to. You'll recall at the end of In-memory Evasion, I did show you a built-in PE parser. It's part of Cobalt Strike. Now that's still available with the dump verb to PE clone. So we're just going to go ahead and run that. And here's all of our nifty stuff. And what I'm looking for in this thing is rundle entry. That's the exported function in this havex sample. And what we're going to do is just replace the reflective loader string with that. You know, again, just giving a little bit more, a few more clues, if you will. And we'll get rid of the old compile time we had, and that's it. Now our havex sample is, our havex profile is updated to look more havex-ish by taking on some of these false flag indicators from an actual havex sample. All right. Now that we've got the thread emulation piece out of the way, let's go into the evasion features. I'm going to start by refreshing your memory on which steps are taken to get a beacon stageless payload into memory. First, an artifact, which could be an executable, could be a macro, something that launches your beacon. That artifact allocates memory in a process, and that could be the current process, could be a remote process. The artifact then copies the beacon payload stage to that memory. The payload stage is a executable blob whose purpose is to initialize and pass execution to our beacon payload. The artifact then creates a thread to run that executable blob that initializes and passes execution to our beacon payload. What does that blob do? Well, that's documented in steps 9 through 11 here. The self-bootstrapping blob is actually a reflective DLL. And the thing that executes is the reflective loader. And the first thing the reflective loader does is it allocates memory for our beacon DLL. This is the final place it is going to live in that process. It then initializes the beacon DLL in that new memory. Once all of that is done, the reflective loader then calls the entry point for the beacon payload, and beacon starts doing its beacon thing. All right, we're going to work backwards through that process. Right after the reflective loader initializes beacon in its new memory, and right before it passes execution to beacon, the reflective loader has an opportunity to apply an obfuscation. Okay, so here, this is our opportunity to decide, do we want to look like a DLL or not? If we do, we really want to look like a memory-injected DLL, then set the stomp PE option to false. And when this option is set, the reflective loader will do no obfuscation. It will just leave your DLL alone. What if you sort of want to look like a DLL, but really you want to look like a memory-injected DLL trying to hide itself? Well, set the stomp PE option to true. And after the reflective loader initializes beacon into its new memory, it will go through and stomp a few critical headers needed to identify beacon as a DLL. And that is the MZ header, the P header, and the ELFA new value. This is not to say good analysts and good tools can't and don't look for this kind of an obfuscation. They certainly do, actually. But this is a way of emulating what some actors do to try to hide the presence of a memory-injected DLL. But what if you really, really don't want your beacon living in its new home to look like a memory-injected DLL? Well, if you're really sure about that, then set the obfuscate option to true. Now, obfuscate has existed before Cobalt Strike 311. Previously, obfuscate would go through your beacon DLL and mask its import table and mask a few other strings that give it away as a DLL. It still does those things. That stuff is still there. In fact, it actually goes through and masks and obfuscates a lot more things. So that's great. But obfuscate does something else. When beacon initializes itself in a new memory and obfuscate is set to true, the reflective loader is not taking those headers over. It's taking none of it. You're just going to get the things needed to execute your beacon, and that's it. No PE header. It's not being stomped out. It's just not being brought over at all. So if you don't want to look like a DLL, set obfuscate to true. So now we have the ability to get a beacon in memory and have it look like a DLL or not really look like a DLL at all once it's initialized. That doesn't do much about another problem we have. And that other problem we have relates to how the reflective loader allocates memory for our beacon payload. By default, the reflective loader happens to use virtual alloc to allocate some memory for our beacon to reside in. Now we can change the permissions of that memory. We can make it RWX, or we can make it a little bit more restricted. So we do have that control. But that does nothing about a problem we have, and that is all executable pages that are not backed by a file are suspect. Now, certainly, executable pages not backed by a file do show up. They show up with virtual machines and just-in-time compilers. They show up all over the place. Okay? But this is something hunt analysts do zoom in on. So, if you want to take that particular behavior off the table, you can take advantage of a technique called module stomping. And what is module stomping? Well, instead of virtual alloc, the reflective loader will instead call load library to get some sort of unused DLL into the memory of the current process. It will find where that DLL lives, adjust permissions as necessary, and copy the beacon, the initialized beacon into it. And that's it. To turn on module stomping, just set module x86 to the DLL you want the 32-bit beacon to load. And of course, there's a module x64 for the 64-bit beacon too. Now, module stomping is a wonderful, wonderful foot gun. And a foot gun is basically a handheld weapon, very well designed for shooting yourself in the foot. That means there's a lot of opportunity to make mistakes and have this great flexibility, this great feature go from being an advantage to a frustrating, why did my beacon crash mess? So if you want to avoid that, here's a few tips. First, the temporary DLL that you choose should export a function, okay? It must also be large enough to accommodate the beacon from the middle. Why? Well, the way Cobalt Strike's module stomping works is the reflective loader will load your PAT-C DLL, and then it will brute force through something called an ordinal, which is basically a way of identifying an exported function by its number, to try to find where that PAT-C DLL lives in memory. And that's where your beacon is going to get written to. Now, a few things to think about. First, if the current process has a chance of loading this PAT-C DLL later, that's really bad. Because if you load that DLL and overwrite it, and it gets loaded and used by something else later, that something else is going to jump right into the middle of your PAT-C DLL and possibly where your beacon is, and it's going to crash. You don't want that. Also, when you choose a PAT-C DLL, look at that DLL on multiple versions of Windows. Pay close attention to the versions of Windows you expect to see during your current engagement, because that DLL might be smaller on an older version of Windows. You might land on an old Windows 2008 R2 server and discover that that DLL is about a third of its size on Windows 10, and that is going to cause a crash. So those are some things to be aware of when choosing a PAT-C DLL. But it's really not that bad. Beacon's reflective loader does a lot of things to try to help you. For example, if the PAT-C DLL does not exist, Beacon will just fall back to virtual alloc. If that DLL is already loaded into the current process, Beacon will detect that and fall back to virtual alloc. And if you happen to choose a PAT-C DLL that Beacon plans to load in just a moment, C2Int knows what those DLLs are, and it will warn you. So these are a few things there to help you out and help you make good choices with your PAT-C DLLs. One thing I'll say about module stomping, just a little tradecraft thought, if you will. I would not use module stomping with my post-exploitation or staging infrastructure. I would use module stomping with any team servers set up to maintain a long-term presence in a network. Why? Well, the team servers set up for managing long-term callbacks, you're not going to be operating on them that much, and you're not going to be injecting those beacons all over the place. There's a lot less risk of one of these things going wrong. And module stomping is great for situations where you just want a little bit of an extra nudge, a little bit of an extra edge at hiding yourself. So that's why I recommend it for long-term persistence operations. So module stomping is great. The ability to initialize our beacon without those nasty P headers is great. But we do have a problem. And that problem is the self-bootstrapping blob that initializes our beacon payload. It's still there. And module stomping doesn't do anything about that. The obfuscations I mentioned a few moments ago don't do anything about it either. Okay? So what do we do about that? I mean, that thing stands out. It's probably, sitting in a blob of memory, in a page of memory that has executable permissions that's not backed by a file on disk. So that's a liability. Well, Cobalt Strike 311 has you covered here too. Set the cleanup option inside of your malleable P block, the stage block, to true. When this option is set, Beacon will call virtual free on the memory associated with the self-bootstrapping blob that loaded it. So this is a way of getting rid of this very unwanted piece of evidence. So that's another option introduced into Cobalt Strike 311. All right, let's take a look at these obfuscations. Here we are in Cobalt Strike, and I'm going to export a stageless beacon executable. One thing I want to note is I'm using the artifact kit, that is the generator for executables and DLLs from the Cobalt Strike trial. And the reason I'm doing that is because the artifact kit happens to use RWX pages everywhere as a default. And I'm doing that so some aspects of this demo can stand out a little bit easier. So we're going to go ahead and save our beacon.exe. It's a stageless payload. And we're going to go ahead and grab beacon.exe and host it on our Cobalt Strike web server. And we're going to call this no evade.exe. All right, so this looks good. Launch. Going to come over to our target system, and we're going to go ahead and just download and run noevade.exe. All right. And there it is in process 2192 as a child of iExplore. If we come over into Process Hacker, go from the General tab over to Memory, and sort by protections. You can kind of see I've done this before. Here we have two RWX segments. Okay. The first, the 340 kilobyte one, happens to be the final place of our initialized beacon payload, right? You can see the P header here. The MZ header here is actually stomped out. That's a default. But you can see some other damning text that gives away the fact we're a PE. There's a little DOS stub. This program cannot be run in DOS mode. Fun enough, the rich header taken from our actual HAVX sample. So that's what we've got here. Okay. And here, this 208 kilobyte package with RWX pages is the stub, the self-bootstrapping package that loads our beacon payload, right? And here you can see this is, again, the same thing, okay? So because this is stageless payload, we don't have a stager. These are the two things we're concerned about, right? The loader and the actual initialized beacon itself. Now, let's go ahead and apply some of these memory obfuscations and see what we can do. So I'm going to come over here to Cobalt Strike, and let's go ahead and just kill this HAVX payload. So right-click, exit, and it's dead, right? Beacon exit, yep. All right, and let's go ahead and open up havx.profile. And here's our profile. And let's do this. Let's turn on obfuscate. So let's set that to true. Let's turn on the module stomping. So module x86. We need a DLL. And for that, I'll jump right back over to our target. I'll pop open a command shell. I'm just going to go over to the system32 directory and look at some DLLs. We want something that is big, something that can very comfortably host our beacon payload. If we choose something that's too small, we are going to get a crash. That's a guarantee. So I'm going to use xpsservices.dll. It's a 1.7 megabyte monster of a DLL. That works for me. So let's come back over here and let's put in xpsservices.dll. And let's do module 64 as well. And let's turn on the cleanup option to get rid of that initial loader as well. And I have the option of turning off the RWX pages. I'm not going to do that though. I'm going to leave them on just so it's a little bit easier to find our payload. Okay? That look good? Yeah, looks good to me. So let's go ahead and check it with C2lint. And you're going to notice we get a warning. I've heard people say they ignore the warnings because they're just warnings. That can be a bad idea. I don't recommend it. If the tool warns you about something, listen to the warning. Here, C2lint is saying, hey, you've turned on module stomping, but you've also chosen to expand the amount of space your beacon needs. And it's asking, will the DLL we've chosen be able to accommodate from somewhere in the middle this new size? And that's something we have to think about and reason about to determine if that's true or not. You're going to find out the same way I'm going to find out because I'm gonna go with it. We do test, right? Test everything before you fire it. So I'm going to ignore this warning, but be aware why it exists. It's just calling attention to the fact that now you have to stuff more than the size of beacon originally into that DLL. You've got to stick this larger defined size. All right. So that looks good. Let's go ahead and restart our team server with our HavX profile here. Let's run Cobalt Strike. Connect to localhost. And again, I still have the script that uses the artifact kit from the Cobalt Strike trial. And the reason I'm doing that is because I want those RWX pages for the package, the self-bootstrapping package, to stand out a little bit better, at least for this demo. So let's go to Attacks, Packages, Windows Executable S for a stageless payload. Let's generate that Windows exe. Beacon.exe is fine. Let's go Web Drive-By, Host File. Let's grab that beacon.exe and we will call it, I don't know, demoevade.exe. Hit launch. Let's grab that entire URL. Let's come over to this VM and let's go ahead and run, download and run our demoevade file. And there it is. Didn't crash. That's a good sign. So let's go ahead and double click on that file. We'll process hacker. Go over to memory. Let's look at the protections. We should find some RWX pages in here somewhere. I promise they're there. We left the option on. And there we are. There's only one package of RWX files, or RWX pages, and that is here inside of this xpsservices.dll. Okay. The actual loader is gone because cleanup got rid of it, so it's not here. And if we double click, we have garbage. Right. This is the code for beacon somewhere in here. But there's no PE headers. They're just not there. So that's the obfuscate option in action as well. So that's what it looks like. What it looks like to turn on these different obfuscations. And of course, if you turn on set use RWX to false, you won't have any RWX pages here either. So that's that demonstration. Again, here are the steps to get a beacon payload into memory, assuming no stagers. If you're using a stager, I just can't help you. And for all these things, I've taken you through options in Cobalt Strike 311 that can help you do this differently or with a little bit more OPSEC. I hope you enjoy these features. I hope you get a lot of value out of them. And I hope they help you give more interesting exercises and training to your rapidly evolving Blue Team audiences. Enjoy the release. Good luck. And happy hacking.